Boys and girls, if I could have your attention, please. So far, all we know in this chapter, and it seems like it's a lot of stuff. It is kind of a lot of stuff, right? Is we know those three right-hand rules, right? We know that if there's a wire, that the current wraps around the wire. If this is the direction of the current, it wraps this way, right? Okay. We also know if it's a loop of current, if the current is wrapped, if we've got a coil and we've wrapped wire around it this way, okay, that the north pole of this magnet is going to be toward us, yes? Okay, and then the final one is that we know if we've got a current in a magnetic field that makes some angle with it, and this is the only formula we've got, the current goes that way, the magnetic field goes this way, and then this force is into the page, right? And then whatever that angle is, if it's not 90 degrees, it makes it somewhat less, to the point where if they're actually parallel, then there's actually no force at all, right? So 90 degrees gives the maximum force, and then if there's some angle, then it's less than that, right? Okay. And now what we're going to do is we're going to consider the case of a particle, right, traveling through some magnetic field. So let's make a magnetic field. That's what these X's are, right? Okay, so here's our magnetic field, and the fact that I've drawn X's means that you're seeing the feathers of a somewhat curiously four-fletched arrow. Yes? Yeah, don't put four feathers on an arrow. That's fun. But anyway, okay, so you're seeing the tail of it, which means that the arrow is going away from you, and then if you see a dot, of course, it's coming at you, right? Okay, so our convention is dot is from ya, right? X is from ya and dot is at ya. Yeah? Our two directions. Yeah? Okay, now, if I've got some particle, and let's just make it simple, let's make it a positive particle. Shh, be very quiet. Be very quiet. And let's say that particle is moving this way. Okay, that's just like a little current, isn't it? Yeah? Isn't that just like a little current? And it's actually some Q going that way, right? It's like any moving charge is a current, right? So the Q is going that way, the magnetic field is into the page. We would actually predict that there'd be a force like this. So here is our velocity, here is our force, right? And what we really need right now is a new formula, right? So force is equal to, what is it equal to? It's equal to I, L, B, sine theta, right? Isn't it? And isn't current just charge over time? Isn't it? And isn't multiplication and division communistic? Yeah, it doesn't matter what order we do, so it doesn't matter whether we divide the Q by the T or the L by the T. Does it? Does it matter? No, it doesn't matter. As long as you divide by T, we're just dividing by T, right? What is L divided by T? What's distance over time?
Where's the T? Where's the T?
Oh. Did this T become an L? Did I put an L there? Was there an L there to begin with? No, it was Q over T, wasn't it? Yeah. That's good. So I haven't totally lost my mind. I've just somewhat lost my mind. Yeah. So L over T. What's L over T? That's our velocity. So here's our new formula, is that the force on a charged particle is Q, V, B, sine theta. And we're going to do exactly the same thing. QV is like our IL, right? So this thing is our index finger. Specifically, it's in the direction of the V, right? B is going to be our middle finger. Force is still our thumb, right? And then, of course, we have the intriguing possibility that Q could be negative, couldn't it?
Yeah.
So this is where that, oh, but it's an electron, so it goes the other way, comes in. Okay? So I think it's easier to do it this way. Just QVB it and do it this way and go, okay, it's an electron, so it's opposite that direction. Yeah, protons are anything positively charged would be the same direction as you predict. But just like it always is, right? Negative charge always does the opposite of what you predict. Yeah? Yeah, yeah? So don't ignore the minus sign on this one or something like that, right?
What did you predict was supposed to be?
Well, now if you've already made a mistake and then remember that, make another mistake, right? You always want to make an even number of mistakes. So let's practice the direction on these things, and then we have positive particles velocity, angle twixt V and B, derive. Do we need that? Are people writing that down? We don't need that, do we? Do we? I don't know. You don't have to write it down. This is kind of fun. So I'm going to set up our little power supply. Let's see if I can remember. It's 5,000 volts. What could go wrong? Okay. I'm going to ground this side here. Okay, 6.3 volts, I think.
Grounded into a socket.
Okay, let's just test it so far. Hopefully no sparks will fly. The light bulb should come on. Yes. All right. So remember, this is our hot wire, and the electrons. It's going so fast. It's going so fast that the electrons. It's shaking so hard that the electrons, just like when your dog shakes, water comes off the dog. Right? These electrons. This thing is so hot that when the metal shakes because of its thermal energy, right? Electrons are actually kind of bubbling off into the space, and then we're going to actually apply about 5,000 volts of electric potential to accelerate it toward the front of this. Okay. So let's see. I think we need to make. What do we need to do? I guess we need to make the back negative, don't we? And the front positive, because they're electrons, aren't they? So back negative, front positive.
So many wires.
Can I do that? Can I do this? Okay. Let's try it. Turning up the voltage. Now those sparks are flying, right? Is it green?
Yep. Yeah, it's turning green.
Whoa, baby, look at that. That's fun. So that green is the electrons actually flying up there and hitting a little zinc sulfide. And when the electrons hit the zinc sulfide re-emits that energy as green light. Yeah. Kind of fun. And that's the phosphor that they used to use on those old terminals, like the Matrix and stuff like that, right? Matrix is like way after they had terminals like that, but anyway, here we have it. So those are electrons. Which way are the electrons going? Electrons are going toward you. Okay. Now I'm going to take a magnet, and I really am going to take a magnet, and I'm going to take the North Pole. The North Pole's got a little divot in it. I'm going to bring it in from this side. Okay. So which way is the magnetic field going to be? Well, remember, it's away from north and towards south, so the magnetic field will be that way, won't it?
No,
it'll be away from the North Pole. I promise you. Yeah, but it's going to, from here, it's going to go out that way and then come around toward the south. If I put it above the thing, right, but I'm going to bring it in from the side. Yeah? So I'm going to take this guy, bring it in from exactly the side there, right? So let's do this. Index fingers this way. Magnetic field which way? Down, but they're electrons, so they should go negative down. It's like all of physics is on the line here. Okay? If it doesn't go up, I've got a whole lot of explaining to do. Here we go. Coming in from the side. Is the pattern drifting up? Yes, there we go. This is good. Physics still works. Okay, this is good. Now, these guys said, they were saying, well, gee, it sort of should be that way. So yeah, the magnetic field should go back to the South Pole, shouldn't it? Yeah. So out of here, it